So we're resuming our graph of ellipses. So just a reminder that if we have an ellipse, there's a couple things that you'll notice is the plus and an equals 1 over here are your clues that you have an ellipse. So a few other pieces. This is already set up for us to find the center of the ellipse. And remember, it's backwards, so the center is right 4. Backwards, so instead of up 1, it's down 1. So maybe that's the first thing you do is you actually just write out where the center is. Right 4, down 1. Label it. And then from there, you might even look at some of the things and say, oh, well, 49, that's kind of nice. That's equal to 7 squared. Because it's underneath x, that means I need to go from the center right 7. And from the center left 7. 1, 2, 3, 4, 5, 6, 7. So just so you're aware, these are not the vertices because 81 is 9 squared. That's a larger number. Some people might call these the co-vertices, but that's not universal through all math textbooks. So 9 squared is underneath the y, so from the center go up 1, 2, 3, 4, 5, 6, 7, 8, 9. And also down 1, 2, 3, 4, 5, 6, 7, 8, 9. I think you know me by now that I'm not an artist, so I won't grade your work as if you need to be a perfect artist here. But I'll be looking for clues that you understand everything that we've talked about. That looks almost too circular if you ask my opinion. But you could answer certain questions like, what's the length of the major axis? Well, remember the major axis is double the larger, so it would be 18, whereas the minor axis is double the smaller. Well, 7 times 2 would be 14. And just to show you on Desmos, so I went ahead and typed into Desmos, and remember Desmos will not tell you where the center is located, and it won't even tell you what some of the values are off to the side. I'm not sure of why it does that, but you can see some of the values that we talked about where the vertices are located were correct. And this one actually looks like it's elliptical, as it should. And again, I'm not sure why it won't tell me what the co-vertices are, but those should be values that are on the curve. All right. So if you, or when you do this on your own, don't feel obligated to make your graph look perfect. I want to see that you have the correct center, whether you write it out, and you can identify where the vertices are and everything like that, and you should be fine. So as I move on to hyperbolas, a lot of the information is very similar. The difference, though, is instead of a major axis, it's called the transverse axis. And it doesn't matter which number is bigger now on whether it's a vertical transverse axis or a horizontal transverse axis. What matters is which value is first. So if x is written first, notice that we still have a squared here. That means that it's a horizontal transverse axis, sort of like this first one. Whereas if y was written first, because that's the positive term, we want the one to be positive to tell us the axis that way. But everything else is set up the same, and what I'm also going to do is a very similar tactic to show you what happens to get the best graph possible. And yeah, I'll be grading if I can see the center, and you give me the correct vertices, both vertex, and yeah, we'll go on from there. So a lot of this looks the same. For instance, you could rewrite this problem as x minus 0 squared over 4 squared minus y minus 0 squared over 5 squared is equal to 1. And just to emphasize, what makes it a hyperbola instead of an ellipse is that minus sign in the middle. It still equals 1, but now we're looking at that. So the center is located at 0, 0. So if I were to look at my graph, 0, 0. With a hyperbola, we still go on the x-axis left 2 from the center and right 2 from the center, because no, you go left 4 and right 4. I was doing the square root twice for some reason. Now these ones are the vertices, so vertex 1 and vertex 2. Well, let me fix that because that's going to bug me. I'm sure it bugs you as well. That a equals 4. So how do we do a hyperbola? Is this b value kind of like what we did with the ellipse? We still go up 5 and we go down 5, but now instead of putting points here, what I usually do is I put a box, and I'm making it a dashed box, dotted box for a reason. Because if I put a diagonal through my box like this, and another diagonal through my box like this, what I actually create is the best possible graph for the hyperbola. And what I'm talking about is it doesn't quite look like a parabola. It opens up, but it doesn't cross that diagonal that I showed you. And same thing as over here. It opens up. And just like when we did the parabola, you know, we can open up to the left and to the right. And that's what's happening here. And if you're confused why we're opening up to the left and right instead of up and down, it's because the x term was positive. So that's my clue. Since this one's the positive term, it's the one that's written first, we're opening left and right. And again, I can show you with Desmos. There's nothing wrong with using the tools that we have. Oops. X squared over 16. Change that to a minus. Y squared over 25. And right now it doesn't look the same because an actual graph would not show you the box and those asymptotes. They're called slant asymptotes for anybody that's curious. If you wanted to, you can actually create the equation of those slant asymptotes. Because if you notice, we went up 5, right 4. So like 5 over 4x is my slant asymptote there. And I could also have another one that was y equals negative 5 over 4x. But that's a kind of a plus standard for a future math class. So all I need to see is this, but how do you get the best graph is by what I showed you over here. So let me change colors and kind of walk you through the next one. Because if you notice this next hyperbola, it is a hyperbola because of the minus, but it's not equal to 1. Well, we did that in an earlier video by dividing everything by 225. And I did give you a clue as to ways that you can shorten this pretty quickly. I don't know if you noticed, but if you used a graphing calculator, you may recognize, here, I'll just start over, that 9 over 225 is the same as 1 over 25. And there's sort of a shortcut here because these are perfect square numbers. But anyway, I'm just trying to point out that 9 over 25 reduces to 225 reduces to 1 over 25. And the same thing could be said with this one. X minus 0 over 9. 25 goes into 225 9 times equals 1. So as I'm looking at that, the center is still 0, 0. I was trying to emphasize that. So it's the same center as what we had over here. Make sure you label your center. This time, the b value is 5, because 5 squared gives me 25. But notice that its y is written first, so it's going up. So that's where my vertex is. That's one vertex. And my a value is 3. I guess I forgot to go down 5 as well. 1, 2, 3. 1, 2, 3. So how do we get the best graph? Well, what I like to do is make that box just like what I did earlier. Kind of like we were doing the ellipse, except it's a box instead of that circular. And then a diagonal through the corners. So notice that this is going to be a skinnier hyperbola than this one up here. But because y was written first, let's switch back to red. It's an up and down hyperbola instead of being left and right. Let me scroll down so you can get this last one. So I hope you're recognizing that it's narrower than the other one. And before you get busy on that homework, I want to show you what that graph looks like. So let me just hide this one real quick. 9y squared minus 25x squared equals 225. And you can see that it's, at least I think it's definitely narrower than the other graph that we were looking at. But yeah, that's a step-by-step process. And I'm not going to ask you for these slant asymptotes, but it would be nice if I saw them as you work through your assignment right here. And feel free to write down any questions you have and bring them to class.